When you look at the value-added data, one of the questions that comes up is, well, how do we trust that data? How do we know that the calculations that are displayed are actually accurate? Well, there's a value called the standard error that can be used to validate the data. It gives that plus or minus range for the scores that we can use to assure people that the calculations are in fact statistically accurate. So we're going to take a look at some data, and we'll take a look at the standard error and kind of briefly talk about how it's calculated. Let's take a look at a typical value-added growth report. This would be the one used for grades 4 through 8 that take the tests consecutively, like for math tests in grades 4, 5, 6, 7, 8, compared from year to year. And we see right off the bat at the start a value called the growth standard. And keep in mind that value added is not a per student calculation. It's a per group of students, a cohort, a class of students grouped by teacher or race or whatever category that we want to calculate by, students with disabilities. We want to know how that group of students perform from one year to the next relative to the other students across the state. So in this example, these students scored in a positive compared to where they were 2 years earlier in comparison to the other students that they're compared with. In this class, in this case, it is a group of 6th grade students. The top line represents the goal. Well, the goal is to perform at least equal to where you were with the group before. So if we had a group of students that were at a particular level, we want them to at least maintain that level relative to the other students across the state, other groups of students, 6th grade students in other schools across Ohio. Well, right below that is the standard error. That standard error gives me an accuracy for the 3.0. That 3.0 could be 1.7 NCEs, that's our unit for calculations. That 3.0 could be 1.7 higher or 1.7 lower if we're talking about one standard error. And that's what we're going to talk about. We'll do a little quick display of how that calculates. But anyways, we can see all of the different growth calculations on this report and then the standard errors. And in this video, we're talking mainly about the standard error. To get the standard error, we need to know a few pieces of data in our calculations. We have to know how many samples we have, whether it's test samples in this case. We have to know the growth. In order to get the growth, we have to have a point A to a point B calculation, the average, the mean. We have to have a standard deviation, which we'll talk about in the next slide, and then we'll calculate the standard error, and that's what we're going to talk about. But we can't calculate the standard error until we have a few of those other pieces of data. So a quick reminder, standard deviation is a measure used to quantify the dispersion of the set of data. Are they hovered around the mean, like they are here on the left example, or are they dispersed in a wide spread as they are in the right example? We really just need the value of the standard deviation more than we need to know what the definition is. But in this case, the standard deviation represents 68.2% of the scores, how far apart they are spread from the mean. I would use a program like Excel to calculate the standard deviation. It'll do that for you automatically. So once we have that and we have the number of tests that we have and we calculate the mean, we can calculate out the standard error. And let's take a look at that. And first of all, what's the definition of the standard error? Well, it's a confidence calculation or a trustworthiness calculation of the mean. The lower that value, the more trustworthy or confident we are in the calculation of the mean. So I put the standard error calculation here. We have standard deviation, SD for standard deviation, is divided by the square root of the number of samples. Well, the number of samples is our count, or our N size. So let's take a look. We have 3 examples. In example 1, we had 13 tests with an average of 42 on those 13 tests. The standard deviation calculated out to be 29.2. And when I throw those numbers into the formula, 29.2 divided by the square root of 13, I ended up with 8.1 as my standard error. I took that same data and I doubled it from 13 tests to 26 tests, but it's the same. Each score is just used twice, so that I ended up with the same average. What I want to demonstrate is that when I have more students in my data set, I get a more accurate calculation. That standard error drops. I took that set of data, doubled it again, so now I have 52 samples. They still have the same mean, same standard deviation, but the standard error continues to drop. And if I doubled it again, I would expect to see that standard error continue to drop and drop and drop. Where that comes into play is when we look at big districts like a Columbus, Cincinnati, Cleveland that have tens of thousands of students, we see very small standard errors. And when you look and see where those calculate in, you'll start to understand why some of the scores can look the way they look when you are comparing the big districts with the smaller districts. And we'll look at some of those in some later sections of this course. So let's go back to looking at our growth model. So again, the standard error is keeping us from misclassifying. It's taking into consideration the students that have bad days and good days, and it's smoothing that data out. The growth standard, again, is 0. That's our expected growth. We expect our kids to move along at the same rate as all the rest of the groups of students move along. So 0 is our center point. This group of students, in this case, for a 2-year period, had a negative growth of negative 3.2. The DR stands for dark red, and we'll look at the chart here in just a little bit to see where that comes from. The standard error in this case is 1.2. With a standard error of 1.2, and one standard error would mean that that standard error could go above or below 3.2, negative 3.2, so that it could be as low as negative 4.4 or as high as negative 2. That would be our range for one standard error. When we're looking at 2 standard errors, it could drop as low as negative 5.6 and go as high as negative 0.8. No matter what, we aren't seeing a growth above the growth standard of 0 in this case. Let's put that into the chart that they used to calculate the color coding. Now we're down here at the bottom with ours. So we see that starting with one standard error, the data can go as low as that 3.2, negative 3.2 can go as low as that negative 4.4 to a 2.0, negative 2.0. That's our one standard error range. Our 2 standard error range takes us a little bit wider, but both of these fall below the growth standard of 0. If both 1 standard error and 2 standard errors fall below the growth standard of 0, the color coding is red. If the 2 standard error range is anywhere inside that growth standard, is anywhere inside of that, then we're in the orange. If the calculation within 1 standard error falls in the growth standard, as you can see in this, that'll be the yellow. The light green would be that we show a lot of growth, but there's still that possibility where 2 standard errors falls below this growth standard. That'd be light green. And the complete opposite of our red is up here at the dark green, where 1 standard error and 2 standard errors of that calculated growth are well above the growth standard. Doesn't even have to be well above. As long as it is above this line, it will be the dark green. So in our case, it's clear. Even with 2 standard errors, we're still below the growth standard of negative 0.8. Let's put that into the charts that the Ohio Department of Education uses, and even the SAS company that does the calculations uses. With the red, which we saw in our sample, we have significant evidence. That significant evidence is the fact that 1 and 2 standard errors of our growth are below the growth standard of 0, the growth standard. We know there's plenty of evidence to support that. Moderate evidence tells me that, well, within 2 standard errors, we do have the possibility. So there's some growth. So there's evidence. It's not as distinct as the significant evidence over the red. All the way up to the dark green, where there's significant evidence that the school students made more progress than the growth standard. What's the significant evidence? The standard error. That's what they use to provide the proof that the calculations are accurate, statistically accurate. If by chance you need more information on the calculations of standard deviations and standard errors, the internet is full of calculations and examples on how to calculate that. Thank you.